Hey, good morning, good afternoon, and good evening. Wherever you may be joining us from today, we would like you to welcome you to our webcast. Today's topic is on WRF Project 5168, Enhancing Drinking Water Treatment Resilience to Wildfire Events. Before we start our webcast, let me first go through some housekeeping items. You can submit a question at any time through our question box. There will be a Q&A at the end of the presentation. The slides and recording of this webcast will be available on our website, wildfiref.org. You can download the slides now and access a link to the project page under Event Resources on the bottom left of your screen. A certificate of completion will be automatically generated after the webcast. If you have any questions, please reach out to our webcast coordinator, Michelle Suazo, at msuazo@waterf.org. And finally, we do ask that you please stay until the end to fill out a quick survey to help us determine future webcasts. With that, I now pass the virtual baton over to Harry Zhang, who will get you to the real reason you're all here today.
Okay, thank you, David. So I'm Harry Zhang from the Water Research Foundation. So I'm the project manager for this project. So here's the agenda for today's webcast. So there's three parts. So first, I'm going to give a brief presentation on the Research Foundation, the research relating to wildfire impact mitigation. And then Lynn from Brown Caldwell and also Mac from Portland Water Bureau based in Oregon going to give the presentation on the project. And then we'll have a Q&A moderated by Lynn. So here's just a cover slide for my summary. So I want to using three slides give you a quick overview. The first is really I want to introduce Research Foundation has a research portfolio on the climate change and also extreme events. So we have a climate change topic hub. So in that topic hub, there's the summary documentation of the 100 climate-related studies across one water matrix. And then they also group by climate adaptation, climate mitigation, which focus on greenhouse gases, and now climate risk assessment. So within the climate adaptation, we further divide into wet weather, stormwater management, and also the water supply and drought resilience, and also the wildfire impact mitigation subcategory, which is the focus of today's talk. And also there will have one subcategory called a broad approach to climate adaptation. So relating to the wildfire-related research, this slide I just want to give you a quick summary of the Research Foundation completed project, which you can use for your information. And also I want to mention some ongoing or upcoming project. So on this slide, you can see Research Foundation has conducted research on the wildfire-related studies, like treatment resiliency and also distribution system, and also source water protection, water quality impact. I want to mention special calling attention. Research Foundation going to issue one RP. The title is, which is the last bullet here, called Ensuring Resilient Source Water Protection Program under Extreme Event in a Changing Climate. So this also cover wildfire as one type of extreme events. So this is my concluding slide. Just want to mention two publications which are released in 2025 this year, including this one, which you're going to hear in more detail. It's another project focused on distribution system, water quality impact, was managed by my colleague, Dr. Yan Zhang. So I want to encourage you to take a look at those information. With that, let me pass the podium to Lynn.
Yeah, thanks, Harry. Well, I'll introduce myself. I'm Lynn Stevens. I work at Brown & Caldwell, and I serve as our Northwest Drinking Water Area Leader. Mac and I are excited to present on our study, which is talking about enhancing drinking water treatment resilience to wildfire events. This project would not be possible without all of the contributors and collaborators that you see on this slide. I especially want to acknowledge our co-principals investigators, Yona Akagi with the Portland Water Bureau and Monica Melko with the University of Waterloo. This project was co-funded by the Portland Water Bureau and the Water Research Foundation, and our utility sponsors, Seattle Public Utilities and Metro Vancouver, helped collect ash to make the study possible. I especially want to acknowledge Portland Water Bureau staff that were very critical in the pilot study efforts that we're going to talk about today. So with that, here's an agenda for our webinar. We'll discuss the project drivers and our research approach, and then we'll highlight our ash characterization and bench scale testing findings. And then we'll really focus on the pilot scale testing that we did as a part of this project, because that's what's very unique about this study. And then we'll summarize with the wildfire resilience frameworks that we created based on this research. So first, let's talk about the project drivers and our research approach. As many of you know, fire season is getting longer and wildfire severity is increasing in many regions globally. And this is primarily due to warming temperatures and shifting precipitation patterns from climate change. You can see from the plot on the slide that over the past decade, the annual acres burned has increased, especially compared to the 1980s and 1990s. And regions that historically have not been impacted by wildfires are starting to see a greater occurrence. And unfortunately, with climate change, these trends are anticipated to continue. So as water providers, we care about the frequency of wildfires because over 2/3 of our water supplies are in forested watersheds in the United States and Canada. So when we have a risk for wildfire, there's also an increased risk to our water supply sources. And this slide is highlighting what the potential water quality impacts can be from these wildfires. So following a wildfire event, burned vegetation exposes fine sediments and silt that then following a rain event or first flush can end up in source waters. Specifically, we see degraded water quality and increases in turbidity, organics, and metals. And this really challenges our water treatment processes. It causes a need for increases in chemical demand, specifically with coagulants, oxidants, as well as disinfectants. And all of this increases solids loading and can stress the solids handling system. We also see that increased organics can impact our distribution system, DVPs. So why Portland Water Bureau wanted to embark and co-fund this study? Historically, Portland Water Bureau's watershed hasn't experienced a land standing fire in the past 400 years. But in an adjacent watershed in 2020, the Riverside Fire broke out while they were also planning and designing their greenfield water filtration plant. And to not let a crisis go to waste, Portland Water Bureau was proactive and collected 50 buckets of this ash to try to understand water quality impacts and treatability. And that really was the impetus for this work and this project. And so this slide is highlighting the study objectives. There are three. The first was to gain operational treatment insight on how to treat degraded water quality from wildfires, to test treatment strategies side by side at pilot scale, and then to inform operational and design recommendations through treatment resilience frameworks. So in addition to the wildfire ash that Portland Water Bureau was able to collect in 2020, our partners Metro Vancouver and Seattle Public Utilities also contributed ash. Metro Vancouver contributed ash from the Minnetonka Park fire that you see at the top of the image. And then Seattle Public Utilities provided ash from the Bolt Creek and Lac Katrine fires. And then, unfortunately, in 2023, Portland Water Bureau did experience an ash in the watershed, the Camp Creek fire. And so all in all, from these real fires that occurred in watersheds, we collected over 500 gallons of ash. And then we've utilized them in our project. So this slide is highlighting our project approach. It first began with an ash characterization to try to think through how you mix ash with water. And then that protocol was the starting point for our bench scale testing, where we looked at different pre-oxidation and coagulation, strategies. The bench scale work really set the stage for the pilot scale testing, where we compared conventional treatment with pre-ozonation to conventional treatment with pre-chlorination. And then all of this information really, and lessons learned, guided the treatment resilience frameworks. Unfortunately, as much as we'd like to present all of the results from our study, we're limited in what we can present in this hour webinar. And so in the next two slides, we really wanted to highlight some of the assessments that were completed and recommend that you dig into the report to gain further insights and information. So the first column's highlighting some of the parameters that we tested throughout the treatment process, as well as in full run raw water and spiked scenarios. What was very unique about this study was that we did it at pilot scale. So we could look at filter run times and calculate unit filter run volumes. We also assessed biological activity in the filters through ATP. And a main way that we assessed treatment efficacy was through disinfection byproduct formation potential testing. We used different methods, as well as looking at regulated and unregulated DVPs. We also tasted the water to understand if there was like a smokiness flavor remaining and to understand which treatment processes were most effective. And we did that through the taste and odor panel. When you think about wildfire and when you think about organics, there's about much of constituents that are comprising these bulk organic measurements, such as TOC and DOC. And we wanted to understand, how do those organic constituents shift through the treatment process, and how does wildfire impact those constituents? And so we did some advanced organic characterizations. We did fluorescence excitation emission matrix, or EAMS, and then University of Waterloo supported the size exclusion chromatography work that was done for the project. We looked at a bunch of treatment processes. So for oxidation, we looked at pre-ozonation, pre-chlorination, as well as intermediate ozonation. We looked at 3 different coagulants, as well as several different coagulation approaches. Over like 25 bench scale coagulation tests were performed. We also looked at the value of adding powder activated carbon. And then for filtration, we looked at granular media filtration with anthracite sand and examined different loading rates. So now I'd like to highlight our ash characterization and bench scale treatability findings. So one thing we wanted to do was really try to best to simulate in this ash characterization work how a reservoir system would look as ash runoffs the environment, mixes in source water, settles, and then is taken up in the intake of a water filtration plant. We didn't want to try to predict what a specific raw water quality impact would be for a specific site, because that is really dependent on your watershed characteristics, the wildfire severity, and even hydrology. The goal of this work was really to create a range of starting scenarios so we could look at treatment efficacy to those conditions, and hopefully through a broad range of scenarios represent what might happen to a specific utility. This next slide shows our range of water quality that we developed and the average water quality conditions at bench scale. The project developed a specific protocol for mixing ash through that ash characterization work. And so the average values that you see in this plot are based on dosing 10 grams per liter of ash, mixing for approximately 60 minutes, and then settling for 24 hours. You can see the Bull Run raw water unspiked. That's the first column furthest to the left. It's pristine raw water quality with turbidity typically around 1 NTU, and organics, DOC and TOC also around 1 milligrams per liter. You can see that when we added the Riverside ash, that the turbidity increased by more than 2 orders of magnitude, but it didn't have as great of a dissolved organics impact as some of the ashes that are shown on the slide. For example, the Bull Creek had the most significant dissolved organic fraction from that ash, just over 20 milligrams per liter. And then we found with the Minnetonka Park Fire ash that it had more recalcitrant compounds that made it even more challenging to treat than the Riverside Fire, even though its turbidity was lower. This next slide is showing what pre-oxidant demands looked like at bench scale. And wildfire ash exhibited, or wildfire impacted source waters exhibited a higher ozone demand. You can see the raw water or Bull Run water on the plot to the left, and then the Riverside Fire ash represented in the middle, and then the Bull Creek Fire ash on the figure on the right. And we started out using dosages that you would typically see at a full-scale water treatment plant, which are represented with the 0.75 and 3 milligram per liter ozone dosages. We were not able to get a detectable residual after 30 seconds with the Bull Creek Fire ash until we dosed it up to 8.2 milligrams per liter. And so based on this testing, a starting organic level as high as that range may be more challenging for a water filtration plant to treat for an extended period of time. This next slide is summarizing our findings from the ash characterization and bench scale work. Highly recommend that folks check out the report, because there's a lot of good information in the report that we weren't able to get to in this webinar. But what we did find was that wildfire drastically increased the oxidant demand. I showed that in the prior slide, but we also saw that with coagulant demands. And then when we evaluated the 3 coagulants, baric, PACL, and alum, we found that alum produced the lowest turbidity, and we selected that for pilot testing and further evaluation. It was also middle of the road in terms of the dose that it required and its removal of organics, as well as not lowering pH and alkalinity to increase corrosivity of the water. The high ozone demand exhibited at these organic levels may not always be practical. And so in pilot testing, we also investigated sub-demand dosages to see if we could evaluate and assess treatment benefits. So with that, I'm happy to turn the presentation over to Matt Gifford, who's going to talk about our pilot scale testing findings.
Well, thank you so much, Lynn, and thanks everybody so much for joining in with us today. My name is Mac Gifford. I'm a water quality engineer with the Portland Water Bureau, and my role on this project was to oversee the team, lead the team that was doing a majority of the experimental work, including all of the pilot scale testing. And so I hope to walk you through some of the pilot scale results, which were a really unique aspect of this study that I'm excited to share with you for the next 20 minutes. So we actually started by figuring out how to make dirty water. We wanted to take all of that ash that we had harvested from so many fires in the region and figure out how to use that in an intentional way to create large volumes of wildfire impacted water that were created meaningful scenarios that we could later feed into the treatment process. It was kind of a fun exercise. Being a water treatment professional, we're used to making really clean water. It was kind of fun to turn that around and try to make really dirty water for once. But let's take a look at some of the equipment that we used in order to accomplish that. Welcome to the Bull Run filtration pilot shown here. Most of the treatment equipment is in those 2 blue enclosures. This is located right at the intake of our primary drinking water system. And then and then special for this study, we brought in a whole bunch of equipment that was really necessary for trying to do this, doing this wildfire ash spiking study, including these two big tanks out front. The smaller black tank we used to mix up the ash, and then we could pull the supernatant over into that larger gray spiking tank. We also used a whole bunch of different pumps, some pumps there to provide the mixing, and transfer pumps to move it all around, and spiking pumps to get that all this equipment kind of necessary in order to conduct this work up at pilot scale, which was presented a bunch of unique but fun challenges. Let's take a look at how the ash and the water that were used to create these treatment scenarios. We had all of these. We had 90 to 100 buckets worth of wildfire impacted material, I'm loosely calling ash, to use. We were very thoughtful and intentional in knowing how much ash to mix into how many different batches of impacted water that we made up. We could fill up. There's one picture there down in the bottom center of like filling up. That's looking down inside the tank, and we're filling that up with raw water directly from our intake, with a sump pump down in there that's starting to provide some agitation for mixing, but really tries to capture some of the scale of how big some of this effort was. And then we can look at the mixing and the settling. So over there on the left, you can see where those sump pumps are kind of buried in there, but are providing agitation and mixing energy. This is similar to what might happen is after ash runs off into streams and rivers and is providing mixing energy, and those water quality impacts are imparting into the water. And then after, and we're very intentional using results from our ash characterization bench scale studies to know how long to mix it for before we shut those pumps off, and let the water settle. This is similar to what might happen in an online reservoir or a lake, where the heavy dense material kind of falls off on its own, but that lighter fluffier material and those water quality impacts that have been imparted are going to partition off into the water. And we took that supernatant and fed it off into the pilot. But very dirty water is kind of the takeaway here. And that's a challenging day if your intake looks like that. We were successfully able to create some meaningful wildfire impacted scenarios. So compared to our raw water there in the gray, we made up three different, we spiked this ash impacted water in three different phases, in three different distinct spiking phases. One dominated by the Riverside fire ash, where we did see some lower, and this one was meaningfully created to produce a sort of a low impact, but like more chronic, long-term trade-off with turbidity and TOC and other water quality impacts, going up to a moderate impact scenario using the ash from the Minnetonka Park fire, and then that high impact scenario with the ash from the Bolt Creek fire. There were trade-offs here with like how much, these are not super crazy high turbidity or TOC numbers by absolute standards we recognize, but they did provide meaningful scenarios with which we could challenge our treatment systems in ways that we had never done before. And similar, the takeaway I think here for operators of treatment plants is that in a post-wildfire scenario, your treatment plant, you might have to figure out how to use your treatment plant in a way that you don't have any historical knowledge or historical experience to draw from. All right, let's take a look now at pilot treatment and how now we've got the dirty water. Let's figure out how to make it clean again using the treatment equipment. If we looked inside these enclosures here, we've got here are the treatment skids. These are customized treatment equipment procured from Intuitech. We have an oxidation skid, flocculation sedimentation skid, and then a filtration skid. We also did some of the bench scale disinfection afterwards. And we're going to step through kind of like what we learned through each of these steps. What's great about doing this work at pilot scale is you get to see the interconnectedness between treatment processes. By seeing in a complete treatment train, you get to see how one kind of relies on the other, and changes here have effects here, which is really great. We also had dual treatment trains, parallel treatment trains, so that we could conduct a comparison side by side. So here's the process view of how we set the pilot up in order to do this experimentation. With the top train, with one parallel train, using pre-chlorine as our oxidation approach. And then we could compare that to the second train along the bottom there that was used pre-ozone as the oxidation approach. And so we could get a side-by-side comparison of those two different pre-oxidants. Both trains used a mirrored coagulation approach to ice so that wasn't a variable. They both used aluminum sulfate, as Lynn described earlier. And then each train had 2 filters. So our first research question was, which oxidation approach provides resilience to wildfire? Our second research question was, what about filtration rate? And so each filter has 2 filters you'll see that were online, but operated at 2 different filtration rates. One filter operated at a higher filtration rate that might represent like a summertime demand or your production rate that you've got going into your degraded water event. And then a parallel filter operating at a lower filtration rate that might represent more like a wintertime demand or an intentional turning down of your production rate as an operational response to your degraded water. So we're going to keep an eye on those 2 kind of variables there between pre-oxidation and filtration rate. And let's step through each process. Let's step through each treatment process and see what we can learn from each one, starting with pre-oxidants. So here on this slide, now we've got decay curves for demand and decay curves for pre-chlorine on the left and pre-ozone on the right. And showing the applied chlorine dose and how that the residual went through the treatment process, and then the pre-ozone dose on the right, and how that went through the contactor. The real quick takeaway is that both oxidants really got absorbed very quickly in these high organic scenarios that are possible after a wildfire. It absorbed a lot of that oxidant really quickly in both scenarios. For the chlorine, there was very little. We applied doses of up to 1 milligram per liter. We don't want to go much higher than that. We're not trying to provide CT. We're not trying to provide disinfection here. We're just conditioning particles in order to be removed in subsequent treatment steps. So that residual was mostly gone by the time we got through rapid mix, and then by the time it was hitting the filters and coming out of the filters, it was mostly non-detect, which was fine, which is what we wanted. Ozone decay, we were usually applying around 1 milligram per liter. For short periods, we spiked it clear up to even 14 milligrams per liter, and still couldn't really detect much of a residual by the time our first detector there at 8 minutes of contact time. The takeaway message here is that a pre-oxidant, even if it's consumed, it does still provide downstream treatment benefits, even if it doesn't carry a residual for very long. Now let's take a look at coagulation. Here is, after lots of work, this is our decision-making process that we used to find the right coagulant dose. As a treatment plant operator, when you're running a pilot, when you're responding to degraded water, your coagulant dose and decoagulation approach is really the most control you have. It's kind of one of the most critical things you have to really manage. And so here's our kind of decision-making process in responding to these challenging scenarios that we found to be really helpful. Starting off with finding a correct coagulant dose. Here, zeta potential ended up being just one of the most valuable tools we could find in order to respond to these degraded water scenarios. Zeta potential allowed us within 5 to 10 minutes to get a really quick answer on whether your coagulant was properly destabilizing your water, and tell you whether your dose was right or not. A lot faster than kind of like traditional jar testing approach was. For the Riverside round, this was the low impact scenario. That was sufficient. Once we got the zeta potential into the right window, everything worked. The settleability came through, the filterability came through, which was great. Now for the moderate impact scenario with the Minicata round, we had to go to step 2, and that was pH and alkalinity control. So the next thing after you've neutralized your charge, after you've found the right zeta potential, you move on to pH and alkalinity control, and you make sure that your rapid mix is in the right operational window for the coagulant you're using. For alum, we needed to hit in between this kind of window. And once we got there, then the filterability and the settleability worked out well for that second Minicata round. For that high impact most challenging round of using the Bolt Creek ash, that's the fire from Seattle, we had to go to step 3 down there If we're still struggling with high solids or high turbidity or short filter runs, that's when you add a little bit of coagulant aid, where some cationic polymer can offset your coagulant demand a little bit, provide some bridging and improve your flocculation, your coagulation. And in that case, once we added that, even in this most challenging scenario, we were able to properly coagulate our water. And hopefully this is a good resource that treatment plants can use to kind of step through operational response to a degraded water scenario that they're not familiar with. The one other thing that's worth mentioning in talking about coagulation is just the volume of solids, the massive solids that are going to be generated. All of the post-wildfire scenarios that we tested involved a lot of solids and producing a lot more solids than were normally observed in baseline, compared to some of the gray bars here, which is sort of our baseline case where we're used to only dealing with 5 to 10, 5 or 6 milligrams per liter worth of TSS. Even our peak solids, we were producing up to 100 milligrams per liter, 120 milligrams per liter, 30 times more solids than normal. Even the long-term chronic conditions, we're still producing something like 5 times more solids than a standard condition. Most of that was removed through settling. It was gone by the time it got to the settled water, which is what settling basins are for. But it gives you an indication of like what that treatment facility needs to be ready to handle to respond to these challenging scenarios. All right, let's go on to filtration next. We're taking a look at our pilot filters next. And this is one of the parts I'm kind of most excited about, because this is one of the things that's really difficult to see at bench or full scale, but was really able to shine through at pilot scale. Let's take a look at filter runs. Right here, we're looking at one filter run. This was from the Riverside round. That was the ash that Portland collected. Now, a filter run is being shown over time. The black dots here are the filter effluent turbidity that we're trying to keep below, definitely below 0.3, even ideally below 0.1. The blue dots are particle counts in the filter effluent. That red line is your head loss accumulation that increases over time, going from your clean bed head loss up to your terminal head loss. And the shaded area is when the spiking was active. We had about 60 hours worth of, we were able to spike the water for about 60 hours. With that long-term scenario, with that ash before it ran out, and then the filter run kind of continued on even past the 60 hours. So the first takeaway, now if you let me skip over that little blip, there's an interesting blip there I'm going to talk about here still, but if you let me skip that for now, the first takeaway is that we were successfully able to make clean water, which is super exciting. We made very dirty water. Here's the proof we were able to make very clean water. Filtration works, treatment works, which is exactly the resilience we were hoping to demonstrate. But this demonstrated being able to meet filter effluent turbidity and filter effluent particle count goals over an extended duration, meeting minimum runtime and minimum productivity goals as well, which was awesome. Now I'm going to throw up 3 more filter runs here also, and now we can compare with all 4 of these filters that we're running simultaneously. Here's a little bit of what was happening in all 4 filters that were running at the same time. The top 2 graphs are the pre-ozone filters. The bottom 2 graphs are the pre-chlorine filters. The 2 on the right are the ones that are running at a really high filtration rate. The 2 on the left are the ones that are running at the lower reduced filtration rate. And we can see some really interesting comparisons as we look between those 4 filter runs. And now we'll go back to that blip. Wait, what happened there? At about 16 hours into our spiking study, you'll see all 4 filters had this little spike up. That was a coagulation error. We accidentally overly coagulated our water. We missed our coagulant dose for a little bit. And we were watching our filters, and we saw that filter effluence turbidity start to spike up. That had made us realize there's something wrong. We got to go fix something. We found it. We took a zeta potential reading, and we made our coagulant dose adjustment. And it takes some time for that water to work through before the properly coagulated water gets back to the filters. This provided a really interesting lesson, though, in seeing how the different filters responded to that process upset. The 2 filters on the left, the 2 lower rate filters, you see they spiked up, but they held on. And once that properly coagulated water got back, they stayed within spec. Once that properly coagulated water got back to them, they came back down, fell right back down to those really super low turbidity levels that you'd expect, and they continued and finished their filter run, really demonstrating some increased resilience to an upstream process upset. Unfortunately, both of the two high rate filters, the two graphs on the right, they spiked up above the 0.3 NTU limit that we had. That meant that terminated their filter runs. They both went into backwash, and we lost the production out of those for 30 to 45 minutes as they backwashed. So those filters had to be taken offline. They backwashed. By the time they were done and ready to come back online, the properly coagulated water was there, and then they continued to show that they worked from there on out. So when they got the properly coagulated water, they also met all the filter productivity, filter effluent water quality goals, which is excellent, showing that both filtration rates work. But this was a great example of how slowing down your filtration process, slowing down your production rate, really gave you an increased operational window, really gave you increased flexibility for responding to a degraded scenario, which was really, really super interesting. Now I'm going to take that same data from the last slide, and I'm going to convert that into UFRVs. And this graph here is showing us unit filter run volumes, which is normalizing both run times along with production rate, so that we can make comparisons between the filters that were operating at different filtration rates. And this one's now got, so those 4 runs we were just looking at turned into the 4 orange bars here, but I've also added in the results from the Minikata and the Bolt Creek rounds from the other 2 rounds of spiking. And to see some interesting comparisons, again, between the pre-oxidation approach and the filtration rate approach. We want more productivity, so higher is better. And what you notice is that the 2 outside sets of bars, those are the 2 lower rate filters that are kind of on the outside, are higher than the 2 sets of bars in the middle. So what that tells you is that the lower rate filters were more productive than their higher rate counterparts. So even though they were only producing water half as fast, they also lasted. Let me say that again. Even though they were only producing water half as fast, they lasted more than twice as long. So increasing their overall productivity. So that's why they had 30 to 130% more productivity at the lower rate. And again, showing kind of the benefit of slowing down your process. Comparing the ozone filters, the 2 sets of bars on the left versus the chlorine filters on the right, what you see here is that the chlorine filters, the ones that got pre-chlorinated water, have higher productivity. They were somewhere in the neighborhood of 10 to 40% more productive than their having higher run times than their pre-ozonated counterparts, which is a benefit of using chlorine as your oxidant. There was a trade-off there, though, with organics. And so here's the slide on organics and how bulk organics, TOC and DOC, this is the bar graphs showing through the treatment process of TOC and DOC, and then the dots are capturing ultraviolet light absorption at 254 nanometers. And here what you see is that the ozone filters did, that both the chlorinated filters and the ozonated filters removed the organic, met all regulatory and water quality standards for removing the organic material out of the spiked water and back to acceptable levels and getting acceptable percentage removals, so that both the chlorine and the ozonated strategies worked. But the ozone here really shows its value because especially the UV254, you'll notice, is about half in the pre-ozone filters compared to those pre-ozone filters. So that sets up an interesting trade-off between the pre-chlorine filters that are lasting longer versus the pre-ozone filters, which are removing additional material and additional organics, and therefore running slightly shorter. And that also shows up in disinfection. And so now we took some of that filter effluent water, we ran it through a DBP assay so that we could get an idea of disinfection byproducts. The full report, you should go check out the full report if you're really into DBPs. We've got some results using uniform formation conditions here. We've also got results from simulated distribution system conditions and both regulated and unregulated DBPs, including haloacetonitrile, some interesting things. But let's take a look just briefly at our regulated DBPs that were created in our uniform formation conditions. So that top graph is our haloacetic acids. That bottom graph is the trihalomethanes. And they were able to compare how the the pre-chlorinated filters in the middle did versus the pre-ozonated filters on the right. In general, we didn't see any difference between high rate and low rate filtration. There really wasn't much difference in terms of dBPs on the filtration rate, but you do see that because the ozonated, the pre-ozonated filters were removing more organic material, you see that they had about 50% lower dBPs than their chlorine counterparts. And the chlorine the chlorine filters did still have 50% as much dBPs as the spiked water. So all met regulations and standards. You got additional benefit with ozone. All right, I'll summarize really quick. Just taking away the pilot lessons learned. We successfully made really dirty water in meaningful and intentional ways that challenged our treatment processes. And then we demonstrated making really, really clean water that met regulatory and customer expectations. Going back to our research questions, summarizing our research questions of what about the two different preoxidants, both using pre-chlorine and using pre-ozone as oxidants successfully demonstrated treating water and providing resilience towards responding to a post-wildfire scenario. The trade-offs, the benefits of using pre-chlorine was that you got slightly lower coagulant doses. I didn't go into that here, but slightly lower coagulant doses. And you got those extended filter run times. The benefits of using pre-ozone was that we had lower organic carbon in the finished water, which resulted in lower disinfection byproducts. And they had also the pre-ozonated filters also rated best for taste and odor. And our second research question on comparing filtration rates. Here's our table. Both the high rate filters and the lower rate filters were able to meet filter effluent particle count and turbidity goals and productivity and filter runtime standards, which was great. So they're both viable options. But the benefits of slowing down your process, using your lower filtration rates, that did increase your productivity, increase those UFRVs and your runtimes, and was more resilient against upstream process disruptions, gave you a larger window to operate within. The benefits, I would say, of using the higher filtration rate, sticking with the higher filtration water, is that you're able to process water more quickly if you need to keep people in water, keep the system pressurized, and it also responded to treatment adjustments more quickly. All right, I think that's it for me. So I'm going to go ahead and turn it back over to Lynn to give us some summaries of the frameworks that we developed.
Yeah, thanks, Mac. So we looked at treatment resilience frameworks, and we broke this down into 3 categories: monitoring tools and assessments, operational responses, and then infrastructure improvements. And we'll highlight each of these 3 categories and how they can build into a wildfire response plan. So let's start out with the first, which is monitoring tools. Specifically, the report highlights which parameters are most beneficial and at which locations to monitor them to inform decisions and operational adjustments. It's important to develop thresholds that, when exceeded, you would make a change in your operational approach, or potentially even shut down and rely on a backup supply. Monitoring really starts at the watershed so that you can be as prepared as possible to potential shifts in source water quality. Additionally, by monitoring water quality in the watershed, it may allow you to employ BMPs to reduce the impact to your source water in the first place. So this can include water quality monitoring in tributaries, looking at runoff impacts from burned and unburned areas, and then online monitoring in your source water itself. What we saw with significant degraded water quality was that you can see some dramatic shifts, and it's important to understand as well your instrument calibrations. So, for example, is your raw water turbidity really at 20 MTU, or did you just max out that turbidity range? So assessing the calibration range for your instruments, as well as increasing the frequency of verification, is important. We found that turbidity and especially particle counts were extremely useful in understanding treatment efficacy. Particle counts were the leading indicator on our filters, as well as correlating well with the amount of solids we were producing with our chemical additions. As Mac highlighted, zeta potential was really most critical in helping us dial in our coagulation approach, not just at pilot scale, but as well at bench scale when we were trying to shift coagulation approaches entirely and doing jar testing. Another thing to highlight is that as your water quality potentially degrades, you can find constituents in your raw water that are not normally of concern, which may require additional monitoring and verification. In a few scenarios, we saw elevated levels of metals, specifically like arsenic and manganese, that exceeded primary and secondary MCLs. And as well as what you've seen with these elevated organic concentrations, that would require additional monitoring and removal verification. It's also important to think about how your water treatment plant is interacting with your distribution system. And so monitoring the distribution system storage levels and thinking about whether you should maximize those so that you can slow down your plant, or whether you are in a low demand period, you actually need to lower those to reduce your water age because of DBP concerns. The next slide is highlighting operational responses. And really a big takeaway from this study is that there's value in slowing things down and allowing more time to react. And so what we saw was both filter loading rates were effective at, as Max said, at producing high water quality, but the lower filtration rate could handle an unoptimized coagulant dose as well as a brief equipment outage. And so thinking about that for your facility and slowing things down and then recalculating your hydraulic residence time, understanding as you make a shift in a coagulant dose, how long will it take for that shift to be seen in your filtered water quality? One option that we proposed is to have one filter at a higher rate to be kind of more your canary in a coal mine and understand the sensitivity of your dosing strategy while operating the rest of your filters at a lower rate for improved resilience. This will also potentially allow for understanding a quicker time period if your dose is off. The next slide is a resource that we produced for this project, and it's highlighting operational trade-offs. So this is showing, assuming you're starting with coagulating with alum only, the left column shows different treatment challenges that could be occurring. And then the first row is highlighting potential operational responses. So for example, if you look at the third row down, excessive solids production, that is a potential challenge that is occurring. You could look at underdosing your alum coagulant, and that would help reduce your solids production, but there could be a trade-off in your treatment efficacy. You can see that there's a check mark with adding coagulant aid, with in combination and adjustment of dosages, you would produce less solids while still maintaining your treatment approach. We think that this table is a resource that we recommend you check out. It's even expanded in the report, and hopefully it could be a standalone reference for operations. The next slide is highlighting infrastructure improvements. Depending on what treatment processes that you have right now, there may be changes that you want to make for increased resilience. The report walks through each of these options and some considerations. All of the ash impacted water quality conditions that we explored in this study would exceed the turbidity requirements for unfiltered water supply. Many water sources in the Pacific Northwest have very low solids and turbidity and are amenable to direct filtration. However, as wildfire degrades source water, we saw very improved resilience from having sedimentation. And so this study demonstrated the benefit of these different processes, and I recommend you dig into the report more so you can learn information about each of these infrastructure improvements. Okay, so what can you do? As demonstrated through this study, it's important to be prepared for wildfire events, and they can be very site-specific and cause varied impacts to source water quality. A wildfire response plan can really help you prepare to think about how you're going to react to immediate impacts as well as prolonged long-term water quality impacts. Components of this wildfire plan can include prioritized lists of treatment modifications based on defined trigger points, critical monitoring and control points, having SOPs in place. We developed a few scenarios that were challenging to treat, that would be for an extended period of time. And additionally, wildfire could impact our water infrastructure in our forested watersheds, like impact it itself. And so it is important to think through what is your backup or alternative water source or emergency connections that you have in place. Communities rely on safe and reliable drinking water, even during an emergency like a wildfire, and responding to those emergencies can be challenging and create a lot of pressure for operators, engineers, and managers. There's a great benefit to planning and preparing as much as possible before the challenge occurs. This study looked at how drinking water systems can increase their resilience to wildfire by investigating different treatment approaches. And so the best defense against a wildfire event is develop a plan and how your utility will help prepare. And so we encourage you to look at our report, to look at the different treatment processes and their efficacy, and to see what could work best for you. So this slide shows a QR code for the foundation report. There's also been interest from other media, including Oregon Public Broadcasting. And with that, we would like to open it up to questions. I know some of you have been posting them in the chat. We appreciate you taking the time to listen to our presentation. So with that, we'll open it up to Q&A. Mac, do you want to take the first question?
Yeah, for sure. Let me give Lynn a chance to take a breather. I think the first one I'll address, I see a couple questions on wildfire, some of the wildfire scenarios, including question on volcanoes, and are these applicable to volcanoes? What about mixed fires that has both, forested material as well as anthropogenic material that's burned? I think the takeaway message here is that we did focus primarily on forested fires and wildland fire, but it's worth asking the question: why are we studying fire? Why is it important to study fire? Of all of the climate change events that all of our utilities across the globe are facing, what's unique about fire is that it can have very similar impacts to treatment as almost any climate change sort of event you can think of, whether it's flooding or extreme weather or cold or heat but the impacts towards water quality and then the subsequent impacts to treatability, when you study fire, you kind of get all of those. Fire impacts, particles and turbidity as well as organics, and a whole host of other things. And so to channel Monica here, this is a phrase that she uses often. When you study fire, you study the ability to reply to any climate change exacerbated landscape disturbance. And so does it apply to volcanoes? Yes. Does it apply to mixed fires? Yes. Hopefully what we've been able to do is create meaningful scenarios. Now, we were not being predictive. We were not trying to say this is the water quality that will come into your treatment plant. There's too many variables there, slopes and fire regime and watershed characteristics. All those things are too site specific to really predict. But we were able to create meaningful treatment scenarios that illuminated trends in the treatment where we could identify what the important places to increase your resilience to be ready for any number of climate change impacts. So that you can increase your resilience to any number of climate change impacts.
Yeah, thanks, Mac. Similarly, there was a question around whether this study was just for surface water systems or would groundwater under the influence also get value from this study. And I think there is value for groundwater under the direct influence of surface water. Those systems may have more of a buffer to a first flush, but you'll still see a shift in raw water quality as well. So this response may be more similar to what we've seen from long-term sustained impacts to source waters, prolonged elevated turbidity or organics. So therefore, the treatment approaches that we looked at today, I think are still applicable to some of those starting water quality scenarios. And depending on the treatment employed, if it's like a package system, for example, there could be more challenging impacts or more frequent backwashes if that is the treatment technology that's employed. Great. I love the questions that are coming in, and please keep them coming. We'll try to answer as much as we can in this time frame, but Mac and I will follow up on all the questions that you ask.
Lynn, I see a couple of questions on zeta potential. I can try to answer those if you'd like.
Go for it,
there was
Mac.
one question on whether zeta potential is affected by oxidants, and another question on what's the difference between zeta potential and streaming current. I will say that for sure that oxidants do affect the zeta potential of your water. And in fact, the two different pre-oxidation approaches did affect, and that displayed itself in coagulant demand. And so if you dive into the report, you can kind of see what some of the different chemical demands associated with the different approaches were. It was a minor impact, but the compared to no oxidant and then pre-ozone and pre-chlorine did have different impacts towards the zeta potential. And ultimately, when you're talking about zeta potential, you're ultimately talking about coagulant demand that was exerted to on the plant. And there were some minor impacts, so it is definitely there. With ozone taking a little bit more coagulant, removing a little bit more organics, and having a little bit more polished water generally was the trend in all of the scenarios we tested. Was there a difference between zeta potential and streaming current? There really is. Those are not the same thing. So streaming current is really good at being, in my experience, and I'm not I'm not selling instruments for either one, but in my experience, streaming current was very good at giving you a real-time indicator if something had changed, if something was going afoul, or if something was different than the last time you looked at it, which is a great red light alarm to have available. The zeta potential we found to be a really good tool at finding out whether you were right, whether the dose you had was correct for the situation you were currently in. So one kind of told you whether you were right, one kind of told you whether it had changed. And so they both have their place. Both of them add increased resilience and ability to, they both have their role. And either one, I think, increases your overall ability to respond to a challenging scenario.
Thanks, Mac. So there's a question on whether there were samples that did not contain ash for the DVP portion of the studies. And there was. We looked at disinfection byproduct potential formation for the Bull Run raw water unspiked, as well as following spiking. And so we did look at formation through each of the treatment processes too. So you could see if you didn't have any treatment, but only disinfection, what that would have looked like with these starting water quality scenarios. And then you could see the impact of different treatment approaches too on the DVP formation. So I highly recommend you check out the results to see if that answers your question better.
Spectacular. I see a handful of questions on sort of watershed management sort of things. I see there's a couple questions on underbrush clearing and watershed management. Those are super important in understanding and managing wildfire risk in any system. Lynn and I are treatment experts. We're not forest ecologists, and so I don't think we have the expertise to tell you exactly what you should or shouldn't be doing in your watershed. Except to say that you should have a wildfire resilience plan, and that a comprehensive plan includes treatment as a response, but also includes upstream things like watershed management and fire risk reductions and fire response planning and interagency collaborations. secondary sources and backup sources of water. All of these are important aspects of having a watershed, a wildfire resiliency plan, and should be part of your comprehensive wildfire response plan. When you're studying that, when you're making improvements. And then hopefully what we focused on here today was on the treatment responses and how to specifically make your surface water treatment more resilient. And hopefully we've illuminated some ways that you can improve that step amongst all of the comprehensive things that should be part of that exercise.
Okay.
Have time for one more, Lynn, or?
Yeah, maybe. Okay, this is going to be the last one. I think it should be this question. It was, thank you for the great webcast. I'm wondering whether Portland plans to apply the outcomes of this project to your practice, and if so, in what ways? So kind of like, how is Portland utilizing this study and this work?
I hope both for my own utility as well as everybody listening in today and everyone who has the chance to read. I hope there was definitely some opportunities to identify places where you can make your treatment facilities more resilient to wildfire. We'll definitely try to see what we can implement into as we're building and constructing and learning to operate our own plant. I hope you find those too, so that all of us can work together to provide what's the ultimate goal here is to provide clean and resilient and reliable water so that our communities continue to experience public health and have a reliable water source, even in the face of changes coming from wildfires into an unknown future. Harry, I think we turn it back over to you.
Yeah, so I just want to let the group know. So the report is the public plus access, I think, which means if you create or have the free Research Foundation account, you can log in and download the report. So that's the message. So, and also thank you for listening, and thank you for great collaboration with Lynn and Mike. I think really this is a great way to getting this project launched and also finished. So thank you.
Thank you. Thanks, everyone.